Completed section 6.3 in the book. As forecasted, this section was a bear, and that's why I couldn't go on, even though I think there may be some little skips in the next few sections. But definitely here I had to do these 46 problems. Near the end, it was fine. I was getting what the QR business, so I was like, fine, I'll move on. Read one section only, of course, this section that I'm talking about here. And then also I am at 1,185 problems attempted in the book. So I'll show the section. So this section is all about orthogonal and orthonormal sets. So you're given some vectors that are not orthogonal or orthonormal, so they can be neither, and then you turn them into an orthogonal set, and then you normalize it and you get your orthonormal set. There's normalization right here, it's explained. And then creating an orthogonal basis or an orthonormal basis. And then, of course, the part that really made the section difficult was the Gram-Schmidt process, where you start off with your spanning set in an inner product space, and then you have a procedure by which you come out with an with your orthogonal set. And so you're constantly having to calculate these inner products. But the thing that really makes Gram-Schmidt difficult for problems is that it's recursive. So if you screw up any one of these in the early steps, and this happened, and I'll show it, then the whole thing is wrong. Unlike other types of problems where you do different parts and they're somewhat separate, they don't really sometimes feed on each other. This whole thing is baked in a cycle, in a recursive algorithm. And if you screw up one of the early vectors, one of the early inner products, or one of the early norms, the whole thing collapses. There's also an interesting case where for your inner product, you're actually doing integrals. And then the whole thing about QR decomposition is there's an intermediate matrix where you take your Q's that are your normalized vectors that are orthonormal, and then that matrix is multiplied by some intermediate matrix, and the product of those two gives you your original A matrix that you started with. Fairly straightforward. Lots of problems. So actually this section took as many pages as the first two sections of the chapter. I actually counted, let me line this up. So I counted, just to get an idea of when the update would be sizable enough, there are 18 pages, 18 double-sided pages in the last update, and I think there's like 19 in here. So this section was a lot of hard work. A lot of mistakes too, because again, as I mentioned, Gram-Schmidt is recursive. So that's my reading, which is the same as the book. Then when I started on the problems, in some cases they were cruised through, but in others they were not. And I'll show a good example of that coming up. So yeah, I also got one thing that I always had to do got better at it as I did it more, was just take out the fraction and then just leave the integers in the vector itself. That made it easy as the calculations got nastier and nastier in the later problems in the problem set. But yeah, so here I forgot a factor of a fifth somewhere. I also forgot another factor. So you have to be very careful how you get one of these problems all the way through. which I did in most cases. Yeah, and in one of them, I tried it. I tried multiple things. They didn't work. I looked at the answer. Okay, it's like, all right, I get it now. I should have done Grant-Schmidt all along. It's in the Grant-Schmidt section anyways. But then I actually wrote down what should have been the correct procedure that I should have used. Yeah, and then of course, when your inner product has different weights, that messes with you in here. That turned out to make the problem difficult because of where you need to leave your factors to make sure that you get the correct factor from the weights. Yeah. So in this case, this is a good example of I convinced myself that I was calculating the second vector correctly. This is not a -1. This should be a -1/2. And I even calculated it correctly here, but it was wrong. So then when I picked it up to do V3, this was wrong until I finally figured out what my mistake was. I also got a little lazy. Sometimes I would forget to come out with my normalized vectors or to do them my own way. That was more complicated by labeling A squares and some other business. The way it's done correctly is a lot more straightforward. And I learned the hard way by making that mistake a couple of times. Yeah. And there was a problem with taking a vector and a polynomial vector and recasting it as Legendre polynomials, and I could do it without doing the integrals. And I tried to do the integrals, and they just didn't come out. So this is going to be for the future, someday, one of those someday. But I could get the correct answer just by looking at them and making sure that I got all the factors. Somehow I couldn't do it the way that they were expecting me to do it, the way Anton wants me to do it. Yep, so that closes out the section. And yeah, once I got to the QR business, it was very repeatable, and I knew what it was. And so I left it there. And then the true-false questions, I only got one wrong, even though I was kind of right, but I did forget that the vectors must be non-zero. But every one of the other ones I did get right. Like, for example, if A is an m by m matrix with a non-zero determinant, then A has a QR decomposition. The key here is that it has a non-zero determinant. So you go into one of those big theorems that we have where all these equivalences, and sure enough, you enter that theorem with, I've got an a square matrix with non-zero determinant, and sure enough, theorem 515G, then A is invertible. And that's what tells you that this is correct. And so from here on out, the next update will be the latter parts of chapter 6.